Hello guys, Cyprien from FE for All. And in the last video I was showing you how to install Salome CFD. Now we will be using it to actually generate a very simple model. So it will be more like a test model and really the easiest, simplest simulation you can do with Code Saturn within Salome CFD. So let's start by opening Salome CFD, and so I suppose that you have installed it successfully. And then let's open the Salome CFD module that I will use after. But first we need to build the model. So click on geometry, and let's build the geometry first. So click on create a box. My box will be 1, 0.1, and 0.01. So it's the unit is not mentioned, so it can be basically you are the one choosing the unit. So if you choose it to be meter, everything you do will be in meters. If you want it to be millimeter, then you'll have to adapt the other units. Here I guess this will be meter. So I click on apply, and one of the things you might notice is that you don't see it. That's because you have to reset the view. So click to reset the view to view your CAD model. And now in this object browser, you see this box appearing. So now we need to create a few things. We need to create some groups that will be used to assign the boundary condition. So what I'll do is that I'll have an inlet on left, outlet on the right. The two sides here and there will be walls, and the top and bottom will be symmetry conditions. So this will be a 2D simulation, but with a 3D model, so I will have only one layer of elements in the thickness. So let's go and do that. So the first thing is to generate those boundary conditions. So let's create groups, and I need to Control and right to rotate the model. Let's select inlet. Let's call that inlet, like that. Apply. Let's select the outlet. Let's call it outlet. Apply. Now let's select two walls here. So I'm pressing shift to select two surfaces at the same time. This will be the walls, and I have top and the bottom surfaces. Those will be symmetry. Okay, apply and close. And so those are the boundary condition, the groups, sorry, where I'll be using for applying the boundary condition. I need a second set of groups, which will be edge groups, and that I will use to refine the mesh and choose the number of elements in each directions. So to do that, there is a function which is pretty useful. It's in operation blocks propagate, and you see that if I select the box, apply and close, automatically I'll have like that compounds appearing. So each of those will reflect this will all be oriented in a specific direction. So this is Y, and I'll just change the name, call that Y deer. So this is Z deer. This will be useful after to choose a number of element X deer. Okay, got it. Now the geometry is ready. Don't forget to save your project. Let's display the box again. So now we need to go to the mesh module, and again reset like that. And now we need to create the mesh. So select the box here in the geometry. Algorithm, so this will be hexahedron IGK. The 2D algorithm will be quadrangle mapping, and the 1D will be wire discretization. and I'll choose the number of segments, so it will be 10 by default. Let's call the name number of segment 10, like that. Apply and close. So if I go forward and I just compute that, so of course it works, but you see that the mesh is not exactly like I want. I want only one element in the thickness, and I want a bit more of element in the X direction. So I'll have to go here and create some submesh, and that's where I'll be using those groups here. So in the Z direction, wire discretization, number of segment, and this will be only one segment. Apply. And then in the Y direction here, I want, sorry, not Y direction. Y direction is fine. It should be X direction. X direction, yeah. X direction number of segments should be, let's choose 24. 24, like that. Apply and close. And now if I right click here and clear plus compute, my mesh looks now much nicer. So I'll need to recreate the groups as well. And I see that by default those groups are created actually, so that's fine. I don't actually need to create. So that's probably a new function of Salome, that the group are automatically created for the mesh when you have those groups. If the group are not created for you, you'll have to use the function create groups from geometry, like that. Okay, so it's fine. I have my mesh. Let's save again, and we'll need to export that mesh. So choose the export as a MET file, and this will be, let's call it channel flow 2. Okay, save that, and we're ready to go into CodeSaturn. Now let's open the CodeSaturn CFD study module, and so there is a small bar that appeared here, so that's the bar that we'll use to create the case. So let's choose an existing study and create it, or create, so check on create, find a folder where you want to save your study and open that. Then we need to give a name to our study, so let's call that channel flow 2 and case 1. So you can call it however you want. This is a CodeSaturn study, and okay. And now you see you have CFD study tree that has been created with some folders into it. So now what you have to do is to open the location of this tree and just put the mesh that I exported before into it. So let's put that into the mesh folder. And now we can open the GUI of CodeSaturn by right-clicking and launch GUI. And here you have it. So let's start by saving the CFD data file. And we'll have to go through all those steps in order to set up the CFD study. So let's start with the mesh. So the mesh directory is okay. Click on the plus, and because I just loaded this mesh into the folder, I can open it here. Now let's see the other thing. Pre-processing, periodic boundaries, others. Well, I don't need that for this study. Volume zone, I don't need that either. Boundary zone, so that's where I'll have to define my boundary conditions. So what I can do is that I can add them, and in the selection criteria, just type the name of my boundary condition. So if I tap inlet, it will automatically recognize the inlet from the group, from the mesh group, which is inside the mesh. The other thing you can do is, instead of doing that, you see you have a button add from Salome. The problem is that if you switch to the tree here, you click on inlet, you go back. Oh, it works. Okay, you can do like this. Switch, click, go back and add. Or if you want, you can just put this window here and you know, add it like this. I find it slightly better, but you know, it's almost the same. Okay, and now that we have those four, let's change also the labels used for this, otherwise we don't know what this will be. So I'll just use the same name, so I'll just copy the selection criteria here and paste it into the label name, so that basically the name of the boundary condition in CFD study will be the same as the name of the mesh groups. Okay, so that's done. Now if you have a lot of mesh groups, what you can do is you can run the solver right now, and because the other things are not defined, it will basically run the solver only on a pre-processing stage, and it will give you some kind of log in which you will be able to extract the boundary condition. So if I go in the Rusu folder, you see I have some results that have been generated, and in it I have a preprocessor log, so I can open that. Okay, I don't know, how can I open it? Let's go into here, case 1 Rusu preprocessor log. So if I open that, this gives you some idea about the number of faces, elements of your mesh and all of that, and it's basically compute, I think, some of the stuff, and you have the name of the different groups. You see family 1, group inlet, group outlet and everything, and you can use this into here, import groups and reference from the preprocessor log. So if you click here and you select the preprocessor log, it will automatically import all the boundary conditions. That's more useful if you have, I don't know, hundreds of boundary conditions and you don't want to click on them one by one. Okay, so that's all for the boundary condition. Now, calculation features. So in this case, it's a simple flow, so it will be incompressible. There's no additional particles or turbo machinery model. All those things are not needed. Turbulence model will use no model. That will be a laminar flow. Okay, no thermal model, no body forces, no specific species transport. Here, volume condition. So in this case, if I want to add up some initialization, no, let me show you that first. This is the physical properties of your material. Then in this case it's for the fluid, so I'll use 1000. So let's use some fluid which is a bit like water. So this will be 1000, and the dynamic viscosity will be this is viscosity, not dynamic viscosity. It's 100. And if you go back here and you select initialization and you come back, you see you have a tab initialization that appears, and this will allow you to initialize the velocity, to set up initial velocity for your model. So in my case, I don't actually need to initialize the velocity, so I'll just inactivate it. Now let me show you how to set the boundary conditions. So if you click on boundary conditions here, by default it's all set up as wall. So I have double click here and set up as an inlet. This will be outlet. The wall, well, it's wall, it's okay, and this will be symmetry. And now I can go on each of those and just set up the right value. So velocity norm, I'll use 2/3, so 0.6667, something like this. Outlet, well, it's I think 0 pressure outlet, so it's not even written. Walls, this will be smooth walls. Symmetry, well, nothing to define either. So as you see, very easy. It's just set up the inlet and that's it mostly. Now let's go on to the time settings. So constant, time varying, steady state. So you have various options. So most simple is to use constant time and the simple C algorithm. So this is for, I guess it's a steady state type of simulation. And this is a reference time step, and stopping criterion will be number of time steps I want to run. So I will run 500 time steps. I guess after 500 I should see some convergence of a solution. Start and restart. Okay, so it's off by default. So this is if you want to stop a simulation and then start it again from that point. Numerical parameters. Okay, I don't need to change anything here. Equation parameters. So here, if you want to change the pressure, velocity, or the type of solver which is used, you can do this, or the scheme used to solve velocity. So for example, you can choose upwind or centered of. So for some kind of models, it's required to change that. So for example, if you have a model made with tetra elements, I think you need to change those schemes, because tetra elements are less accurate, and the Code Saturn solver works. It's a finite difference solver, so it works better with hexa elements. And well, in my case, I don't need to change anything, so that's fine. Post-processing. So in post-processing, let's see, output control. This will output at every time step, so that's fine for me. Or maybe I can set up another value. Output every n time step, maybe every 10, because otherwise 500 time step, it would be a lot. So every time step. In the writer, so this is by default type of format the results will be printed to. So nsite is a default, and I want med, so I'll switch to med to be able to review the results with Paravis. Now you can select also, I think, some type of surfaces you want in your mesh or something like this. You can choose some monitoring points. This is pretty useful if you want to monitor the velocity at some specific points of your model. So let's do that. Let's add a monitoring point. So here it should be 0.05. It gets in the middle, and then I'll just duplicate 1, 2, 3, 4, 5 like this, and I'll set up at a certain distance 0.2, 0.3, no, 0.4, sorry, 0.4, 0.6. It's dark in here. I can't see my keyboard. Okay. Okay. And now you see I got 6 monitoring points on the length of my model, which is pretty cool. Now you can choose if you want to monitor file at each time step, or at every n time step, or So I'll choose each time step. And let's save that. Now let's surface control, so I don't need the stress or the Y+. I will unactivate this. And I'm going to set a profile also, because I want to see the flow profile. So let's add a profile exported at each n time step, so every time step. Click here for the line definition. So this is the expression of my profile. So it will be at x equals 0, so at the beginning here, y equal s, so this will basically a line in the s direction. So if I want not at 0, but at, let's say, at the end of my pipe, so let's choose x equal 1, and this will allow me to see the flow profile at the end. And we need also to put the velocity into it, so I'm getting the velocity profile. Okay, balance by zone, I don't need that. Partition, also this is not required. Okay, save that. Now let's run the simulation. So you can use one processor or several, but if you use several processors, you'll have to have MPI installed. So I think it's using OpenMPI, so you need to have OpenMPI working. So it's simple simulation. So yeah, you see it's already finished. It's so fast. So 500 time step done. Now let's have a look at our results. So let's switch back to the object browser. Let's look at my result folder, and you see that I have one result folder, so it contains my where are my results, post-processing. Okay, so I have two MED files here, so those are the one that contain my result in MED format. I have also the monitoring points that I talked about, and I realized that the profile is not here, so it's a bit strange. But when I looked at my folder directory, I do have these profiles. So I don't know why it's not displaying in here. Maybe it's a bug. I don't know. But you definitely have it. Okay, so how do I load my results? Well, you right click and export in Paravis. So this is a boundary. This is a free domain. So let's export the free domain. And now we have to switch to Paravis. You see I'm looking at my model, and solid color, velocity. Okay, so I'm seeing the velocity at the first time step. Let's view the time step. So let's activate the animation view, like that. Now it's cell results per cell, so that's why it looks like Minecraft type of simulation results. Now what you have to do if you want to get it by node, you have to apply filter. So go in filter, and there's a filter called cell data to point data. That's it. So choose that, apply, and now you see the icon here has changed. If you click on velocity, now you're getting something that looks much more like what we expect from this kind of simulation. Now if I click on play, yeah, I'm actually, yeah, so that's my results. You can look at the pressure, velocity, etc. Now if I want to look at the profile and all this, I can do that as well. So I just have to load and open my profile. So go in results, post processing, where is it? This, not this one. Profile, okay. Apply, and I'm getting them in Excel like this. Excel sheet. So what I need to do is to open that into line chart view. Let's close this one for now, and let's activate this using the eye here. And in this properties window, I can activate or unactivate what I want to see or not. And now I'm getting the profile of the velocity at so I guess it changes also with the time steps. So if I want to get it, yeah, see, if you change the time step here, the profile also changes. So I'm able to see the profile along with time, which is great. And yeah, and if you want to go back and see the view because I closed it, well, you can just click on the plus here and open the render view, and now you just have to click again here, and yeah, it just reappears in this main window. Now, if you're not familiar with Paravis, which is actually Paraview, Paravis is just Paraview with the MED file reader, because Paraview doesn't read the MED file, but Paravis does. So Paravis is just Paraview. I have a full set of videos on my YouTube channel that you can watch to get more in detail on how to use Paraview, because there are various useful functions that you can do. So for example, you want to select some point somewhere here and view the result. Window, selection, display, inspector, and velocity, and now you're able to see the velocity, the three components of the velocity at any point. So, and that's, you can do whatever you want with Paraview, but the first time it's a bit overwhelming. So that's all for this video. So I hope you enjoyed it, and if it was, please give it a like, and also always thank you very much for watching. I hope this was useful. Thank you very much.